In the second half of Chapter 13, we're going to talk about using control variables to help us better understand relationships that we see in contingency tables. And we're also going to talk about analysis of variance. So let's revisit control variables. We talked a little bit about these in the first part of Chapter 13, but a control variable can be added to help an investigator eliminate a rival hypothesis or to further explore the original relationship. The data in the contingency table are divided into subsets based on the values of the control variable. So for example, we might look at the gender, male and female. So we might see a relationship in all the data, and then we might want to further explore it and say, does the same relationship exist when we look within males and within females? For some variables, the analyst will determine the subsets based on the values of interest depending on the purpose of the study. Administrators may want to learn how a relationship changes if other variables are considered. This is referred to as specifying or elaborating a relationship. Does the original relationship change under different conditions? And those conditions are represented by the values of the control variable. Including a control variable is relatively easy. We simply divide the data set into the subsets based on the values of the control variable. So as I mentioned previously, one example might be gender. We might look at males and females. The model will guide the number of subsets created and studied. So for another example is on education. So we could look at education in a lot of different ways. We could look at big buckets like less than high school graduate, more than high school. Or we could go more granular where we could look at some high school, then high school graduate, some college. They got to a bachelor's degree, a master's degree, a doctorate. And here's actually three options here. This one's actually even further exploring, looking at an associate's degree and then a bachelor's degree or higher. So all the bachelor's degree and higher are put into one bucket here. Here's just two buckets, less than 12 years and then high school graduate and above. So it really depends on the purpose of the study. A spurious relationship, an independent variable has been falsely assumed to cause the dependent variable. And a third variable is often introduced to help test for a spurious relationship. The third variable is separately related to both the independent and dependent variable, and if a relationship between the two original variables is spurious, it will disappear when the control variable is added to the analysis. So we're going to look at an example here. The hypothesis is that storks deliver babies. And this is a table from your book, and they looked at the birth rate and whether or not the stork count was high or low. So here's the high stork count and low stork count, and then whether the birth rate was high or low. And lo and behold, what do we notice? We notice that when there's a lot of storks, there's a high birth rate. So it looks like the large number of storks is causing a large number of babies. So this proves our hypothesis. An alternative hypothesis explains why the relationship observed is that the population density is related to both the independent and the dependent variable. And if we add that control variable, we'll see the relationship change. So now we're going to look at the rural counties and the urban counties. So this is where we're looking at population density. So urban obviously are going to be more dense. So now we look and see, what do we see now? Now we see the rural counties have high birth rates no matter how many storks are present. And the urban counties have low birth rates and typically few storks. So now we see that the population density is affecting both the number of storks and also the number of babies. So when we are using a third variable and controlling, four things can happen. The original relationship remains with little or no change in each category of the control variable. The original relationship becomes stronger or weaker in some but not all categories of the control variable. The original relationship may disappear in some or all categories of the control variable, or it could change direction in some or all categories of the control variable. If it disappears in all the categories of the control variable, then we say the relationship is spurious. Original model, this is another example, investigates the relationship between employee age and their annual salary. So here's a possible model. Age influences salary. So age would think the more years of experience you have, the higher your salary would be. Control variable, employee length of experience within the industry, not just their age. Now we're going to be more specific and say how much time did they spend in the industry. The analyst believed that as an employee got older, he or she gains experience. With more experience, they get a higher salary. So they first look at the relationship between the age and the annual salary, and then they elaborate by introducing the control variable and testing it by controlling for the length of experience. So now we've got a 3-variable model: age related to experience related to salary. If the second model is correct, the original relationship should become weaker or perhaps disappear. Because let me go back for a second. What we're actually doing now is we're controlling for experience. So here's another example: an analysis of data on municipal employees to identify characteristics associated with the type of position held by the employee. So the dependent variable was the position type, and we're going to look at 3 types: administrator, supervisor, and non-manager. And then the independent variables are going to be the employee department, the number of years employed, and the sector of the previous job, whether it was private or public, and also education. And our control variable is going to be gender. So here we look at males and females. Here's the control variable. We're going to look at males separately from females. And what do we see? As seniority increases, employees tend to have managerial positions. So non-manager positions are more common when they have less experience. As experience increases, we see more and more going to the supervisor or managerial ranks. Males are more likely to be promoted. We notice here 57% are in a supervisor role when we get more than 10 years, when only 22% of the females are. Another statistical tool that we can use to compare means, now this is an extension really of the t-test, is when we have more than 2 groups. It's called the analysis of variance. And it can also be used to analyze experiments. Some assumptions here: the dependent variables have to be interval or ratio level, quantitative in other words. The variances and the standard deviations for the groups are equal. The independent variable is normally distributed for each group, and the values of the dependent variable are independent of each other. ANOVA examines 2 kinds of variances: within groups and between groups. Within groups measures how much the members within a group vary from the group mean. And then between groups refers to how the mean and the variance of each group differs from the other groups. If the subjects are appropriately assigned to control and treatment groups, the pre-test within groups and between groups are equivalent. If the experiment treatment has no effect, then the statistics for the post-test will also be equivalent. ANOVA is used to determine if the differences between the experimental and control groups could have occurred by chance. So the null hypothesis is always going to be that the arithmetic mean, the research hypothesis, the means are not equal, and the null is going to be that they are equal. And ANOVA determines if the between groups, in other words, is the differences when we go from group to group, is that variation greater than the within group variation. And we use a statistical test called the F-test. If this ratio is much greater than 1, the difference among the groups is likely to be statistically significant. And this has got a lot of applications. It can be used to assess results of multiple regression, can be used to analyze cross-sectional data if the dependent variable is interval or ratio, and the independent variable is nominal. However, you must have samples you have to have random samples. And the assumption of the variance of all groups in the population is equal is often ignored if the sample size in each group is similar. So here's an example of how we can use ANOVA. We're going to do a study to compare 3 job training programs: basic skills, classroom, and on the job. The agency assigns the clients randomly to a program. The analyst wants to see if the clients trained in the on the job program are earning more than the clients from the other programs. Previous research suggests that the on-the-job training participants are more successful, more job ready, and more likely to have better job placements and therefore make more money. So our research hypothesis is that the average earnings of the on-the-job training trainees will be greater after 1 year than the trainees from the other program, and the null is that the earnings will be the same. And we took a sample of clients from the agency records. Interviewers contact the clients to ask for the wage information. And here's what we have. Here's the basic skills training, classroom, on the job. And we looked at the average monthly income. So basic skills was at $433, classroom about $429, and on the job training $765. And here's a nice graphical display. What does the data tell us? Data appear to support the research hypothesis. The on the job trainees appear to have higher monthly income. So 2 questions we can ask. Are the differences among the salaries statistically significant? And if there are differences, which differences are significant? So we do what we remember. We said and analysis of variance. And we look over here, here's the between groups variation here, and the within group, and the F ratio is the quotient of this divided by this. Remember, we said if it's greater than 1, it's probably significant, and it is in this case. It's got a p-value of 0.01. So if the groups had equivalent salaries, we would expect that F ratio right here to be close to 1. However, it's much larger. And the degrees of freedom for an F test, it's going to have 2 degrees of freedom. One goes with the numerator, which is the number of groups minus 1, and then one goes to the denominator. The overall degrees of freedom is the sample size minus 1, and the within groups, is the total degrees of freedom minus between groups. So 2 and 37. So based on the p-value, the probability of seeing an F ratio as large as 5.2 if the salaries were equivalent is only about 1%. Now, given this, we know at least 2 of the groups differ significantly, and we can do what are called multiple comparison techniques, or we can compare means, pairs of means, using t-tests that we learned about in the prior chapter. The ANOVA can also be adapted to include other variables. We can do more than one independent variable, and then it's called a multivariate analysis of variance, or a MANOVA. We can do a 2-way analysis of variance. We can do a 3-way analysis of variance. We can do repeated measures, where we have an ANOVA with more than one measure on a subject. So to summarize, this week we talked about control variables, and we learned a little bit about analysis of variance, which is basically an expansion of the t-test to more than 2 groups, where we want to look at differences among groups.